Hey everyone, you might notice that this is not your usual host for this podcast. My name's Daniel Bashir. I am a new editor over here at The Gradient. I've been working with Andre over at Skynet Today for a bit over 2 years now, and just joined up recently. Today I'll be interviewing Evan Hubinger. Evan is a research fellow at the Machine Intelligence Research Institute. He's also a former lab mate of mine from Harvey Med College. And Evan was an author on risks from learned optimization and advanced machine learning systems. This was a paper that introduced the inner alignment problem to the AI alignment community. So today I'll be talking to him a little bit about his research in inner alignment and a couple of related areas. I do hope you find the conversation interesting and that you'll forgive me for a few vocal flubs. This is my first time interviewing someone for a podcast. Enjoy the episode. All right, Evan, so you're currently an alignment researcher at the Machine Intelligence Research Institute. Before we get into your work on inner alignment, I do want to spend just a little bit of time talking about how you actually got here. So I know you spent a lot of time doing software engineering. I'd love if you could tell me in the audience a little bit about your path towards AI alignment, what sort of turned you on to the issues you're working on. I know you were involved in effective altruism quite a bit before that. So just for our audience, if you could tell us a little bit about what you were doing there, what the EA movement is all about, and how that kind of drove you towards AI alignment.
Absolutely, yeah. So you sort of preempted me in that I did get into into AI safety through effective altruism. So I guess, in like high school, I started reading like the sequences, and I was sort of familiar with like the rationalist space and like some of these sorts of old works like superintelligence and stuff. And so I knew that it existed, and I knew this stuff was happening, but I wasn't really sort of involved in it or thinking it would ever be something I would go into. In college, I started to get into effective altruism. So a friend of mine started the EA club at Harvey Med, where we both went, and she sort of never was really able to get it going. But I sort of decided I would take over, and I ran it the sort of club there my junior and senior year. And then I also, so while I was running the EA club at Med, I went to an EA Global, which is this conference for just like, lots of people who are interested in effective altruism. And I met some MIRI people there. And I had previously done a lot of work in functional programming. So I wrote this functional programming language called Coconut that's kind of popular. And so I had a lot of functional programming experience. And MIRI at the time was doing a lot of just like functional programming software engineering stuff. And so they sort of invited me to do an internship there. And so I did an internship at MIRI, just doing software engineering, the sort of functional programming stuff. And while I was there, I was sort of invited to do this thing called the MIRI Summer Fellows Program, which is a sort of couple weeks long summer research retreat. And I, at the time was not really, didn't really believe that I would be able to do AI safety research. I knew I was a software engineer, and I knew I could do software engineering. Mm-hmm. But I was like, I'll give it a try. I'll see if I can do research. And while I was there, I met a couple of other people, and we sort of, I sort of got a group together to work on this sort of specific topic, which is really trying to, at the time, there's a lot of discussion about this sort of very general understanding of what if we train machine learning systems that had different goals than the goals we trained them on. Where there's sort of this analogy to this idea of evolution of, it's kind of weird that humans don't care about like inclusive genetic fitness or something, despite the fact that we were selected for that. Mm-hmm. And could the same thing happen in ML? This was sort of the state of the discourse at the time. And I found this idea really fascinating. And so I put together a group of people, and we sort of tried to think about it and work on it and see if we could write a sort of paper about this. And this ended up becoming the risk and learned optimization paper, which I think we'll probably talk about some of the ideas in that paper here. And so I published that paper with a bunch of other people that I met at this research retreat. And Paul Cristiano, who was at OpenAI at the time, was really excited about this. And so he, after we sort of published it, he invited me to apply to OpenAI to work with him doing some sort of theoretical alignment research there. And so I went to OpenAI after I graduated, and sort of I was there for a little bit doing some theoretical stuff with Paul. And then when that was done, MIRI offered me a full-time research position, and I've been at MIRI doing research there for the last 2 years.
Fantastic. Well, thanks for that rundown. Before we get into inner alignment specifically, I do want to talk about just alignment a little bit more broadly. And I guess where I want to go with this is I imagine that some of our listeners, or many of them, might be familiar with it. But I also know that there's a good amount of people who are maybe not so sure about whether AI is an existential risk, or unfamiliar with the alignment community, not too sure about its goals or the value of theoretical research. I was wondering if you wouldn't mind maybe taking a second just to try to give a little bit of like an argument or your perspective on why you think that AI safety as a whole, and particularly maybe some of the theoretical work that you all do over at MIRI, is so important.
Yeah, absolutely. So it's definitely the case that like the reason I do this work is because I believe it's valuable and important for the long-term future. I said I got into it through effective altruism. I think I really enjoy software engineering a lot. And I think I don't enjoy research as much, but I really find that it's the way I can contribute most to the world, because I'm like quite concerned about the risks from AI. I think that, really the way that I see the sort of real big existential problems with AI is a little bit different. I think that it's maybe more of and I think that in many ways you can think of risk and learn optimization in this way, and it's sort of become this thing in the sort of space that is like a more modern, more sort of ML focused way of thinking about the existential risks. And it is really the risk and learn optimization style risks that are the ones that I'm concerned about. So I can maybe give a brief overview of what that would look like, but I think really, hopefully, when we really delve into it, I can really go through what is the sort of risk there. But very, very broadly, the risk is that if we train a system, and I like to give this example. So let's say we're training a system to solve mazes. We want to train a model to be able to navigate a maze and get to the end of the maze. Mm-hmm. And, let's say during training, we put a little green arrow at the end of the maze to sort of mark the end. Mm. And we ask the question, what happens when we deploy this model off distribution in a setting where the mazes are larger and the green arrow is no longer at the end? It's now, like in the middle somewhere. Mm-hmm. What does the model do? This is a generalization question, right? Yeah. And so here are 3 different possible generalizations. So one possible generalization might be that the model just didn't learn a general purpose maze solving optimization algorithm. And so when it sees this big maze, it just flounders about. It just doesn't know how to solve it. It doesn't know how to do anything meaningful in big mazes. There's a second possibility, which is that this first possibility where it knows how to solve the maze, I call this capability generalization. It learned a general purpose capability to solve mazes. Okay, there's a second possibility. In the case what I just said was a failure of capability generalization. It wasn't able to learn a general purpose maze solving capability. Mm-hmm. The second case is it does learn a general purpose maze solving capability, and it learns to use that capability for the right purpose. It learned to navigate these bigger mazes to get to the end. And so the way it generalizes from the smaller mazes is that it successfully navigates larger mazes and successfully navigates them to the end. But there's a third thing that can happen, which is that it learns a general purpose maze solving capability. It knows how to navigate these larger mazes, but it navigates them to get to the green arrow rather than get to the end, which is not what we intended. We tried to train it to go to the end, but because the green arrow and the end of the maze were sort of identical on the training distribution, it learned one rather than the other. And, I think the thing that I call this capability generalization without objective generalization. So its capabilities generalized. It learned a general purpose capability, but it didn't learn the right objective. Its objective of go to the end of the maze didn't generalize properly off distribution. And so what's so concerning about this, right? Well, what's so concerning is that this is a situation where we trained a model that learned a very general, powerful optimization algorithm. It learned how to do and act very capably in the world. And yet it learned to use those capabilities for an objective that we never intended it using its capabilities for, nor ever even wrote down. We never even specified this objective. We never even asked it to go to the green arrow. The only thing we ever tried to get it to do was go to the end of the maze. And yet It learned to do the wrong thing, go to the green arrow instead, and to use this very powerful maze solving capability to do so. And so if you imagine replacing maze with the real world, we're training models in this sort of setup. We might be in a situation where we train models that are very powerful and able to take coherent actions in the world, and yet those actions might be directed towards goals that are entirely different than the ones we tried to train the model on, just because our training process is insufficient at actually ensuring that the model goes for the sort of right goal, the one that we intended. And so this is sort of, as I see, the core of where I think most of the existential risk from AI comes from.
That's a really great argument, and I appreciate that. I do think that one of the things that really stuck out to me as I was reading through your inner alignment work was that it felt very easy to map onto even some of our current ML systems, the way that you think about this. And I guess to what you're saying, this also does kind of highlight some of the, I suppose, problems when we think about just the more and more complicated kind of black box algorithms, not knowing exactly what they're optimizing for, what they're learning about, what they're focusing on, can really be detrimental when we start asking them to do things off distribution, because we have no idea what exactly they're going to do. And so I suppose that a lot of what's going on today with model monitoring and interpretability and research on a lot of those fronts, and we can get more into this as we discuss the inner alignment paper, I think you point this out is really related to your research. And I think the fact that we're seeing it kind of open up more today is maybe indicative of how important it's going to be going into the future, especially when we start to see more and more advanced AI systems and possibly ones that have MESA optimizers. I think all that being said, if we don't have anything else prior, I would love to get into that paper itself. And I guess you've given us a really good example here. But I'm wondering if you can go through kind of the main highlights of your risks from learned optimization paper. You've already explained why you think it's important. So maybe we can get into some more specifics about it, things like what is a MESA optimizer that I just talked about, what is impact versus intent alignment. And then maybe as we go on thinking about why would MESA optimizers be even likely? Why should we expect this to be a problem that might arise?
Absolutely, yes. So I'll introduce the terminology MESA optimizer. People who are not familiar, so this is a concept that we introduced in this risk and learned optimization paper. So the idea of a MESA optimizer is, it's really not complicated. It comes from this concept of meta optimization. So meta optimization is a thing that is very common in machine learning, where we train an optimizer to optimize over optimizers. And this is a thing that we often do purposefully. We might do black box optimization over the hyperparameters of a gradient descent process, and then that is an optimizer that's optimizing over parameters of another optimizer. But there is a potentially concerning situation, which is what happens when we do just machine learning, when we train a neural network, we are selecting over possible parameterizations of a function. Machine learning fundamentally is we are searching over possible parameters in some parameter space to find some function which does something that we want it to do. And it is totally conceivable that we could find some set of parameters that itself implements an optimization algorithm. And if we found some set of parameters that itself implemented an optimization algorithm, then we would sort of be doing meta optimization, even though we maybe didn't intend to do so, because now our gradient descent process is optimizing over parameters that are an optimizer. And so MESA is sort of it's Greek, it's just the opposite of meta. So meta is like one level above, one level optimization above. MESA is one level optimization below. It is, we had an optimizer, and then we didn't think it was going to be doing meta optimization, but it ended up doing it. And so the optimizer, the sort of MESA optimizer is the one meta level below the base optimizer. So that's really what a MESA optimizer is. And so we talk about in the paper the sort of situations where how might it be concerning if you have a MESA optimizer? When might you get MESA optimizers? These are the sort of two big questions. So I can maybe start with the why might you get MESA optimizers? I think that fundamentally, the sort of argument for why you would get MESA optimizers is it's that they're simple and they generalize well, right? So if we think about a situation like, let's say we want to train an algorithm to solve Go, right? One thing which we know works really well in Go is search, MCTS. If you have to learn a heuristic to be able to understand what is the sort of is this a good go state in every possible situation? You just have to learn this huge, set of heuristics. But if you have the ability to do look ahead, to, figure out, in this particular situation that I'm currently in, what would be a good go move for me to take? Is this a good sort of situation? You can sort of rediscover what the heuristics are that are relevant in that particular situation by doing this sort of search, this look ahead. Mm-hmm. And so optimization, search is just the sort of thing that is very good at generalizing. It's really good at being able to help you figure out what are the things which you need to do in this specific situation. And so we think about something like AlphaGo, that's a situation where we explicitly gave the model access to search, to MCTS, so that it would be better at being able to solve these sorts of problems. And that is one way in which you might get search. But you could also imagine a situation where we could train search end-to-end, where if you're training an end-to-end, you just have a network, and there are parameterizations of that network that implement search algorithms, and you could just find a parameterization of the network that happens to implement a search algorithm. And this is another valid way of trying to get search out of your sort of machine learning system. Mm-hmm. There is some question of whether we will want to move into a direction where we're hard coding the search or training it end to end. I think that's an interesting question in and of itself. But either way, we are in a situation where we have a model that is doing this sort of really powerful, coherent optimization for some purpose, and we may or may not like that purpose. Now, there's also sort of another way to think about the same thing, which I was alluding to earlier, which is sort of from the simplicity perspective. So we can think about search as a way of compressing heuristics. So if we think about Go, there's a lot of different possible ways of thinking about, in this particular situation, I have to do, this is like a live stone or a dead stone, or all these sort of various heuristics which you need to pick up on to understand what sorts of patterns on the Go board are good or bad. Mm-hmm. But search, trying to actually just do look ahead and figure out which patterns actually survive and which do well and give me points, is a way of figuring out what heuristics to use in any individual situation. And so it's a way of compressing those heuristics into a simple algorithm which reproduces them. And so we actually know that neural networks are very heavily biased towards simple functions. So this is coming from the parameter function map. So the map between the parameterizations of neural networks and the function that those parameters actually encode for, the sort of functional behavior, that map is heavily biased towards simple functions. And there's a lot of research that is that's indicating this. And so we should expect that if we are in a situation where we're doing something like deep learning and we think search is a very simple algorithm, we're going to find these sorts of simple compressed policies because it's sort of biased towards simplicity. And so I think that's the sort of most basic argument. And there are some other things that I can talk about that might push you in one direction or the other. So, another thing might be if we're training models on human behavior, being able to model a human, like humans are optimizers. And so being able to model a human probably requires you to understand optimization enough that you might be able to reuse that same machinery yourself. We can also think about things like, to the extent that the models have the ability to store state over multiple episodes is the sort of thing that seems likely to encourage optimization as well, which is often not the case with a lot of current algorithms where they just sort of, like with a transformer, it has this fixed context window and it can't refer back to some information it was thinking about in its previous activations. But you can imagine future systems that were able to do this, and this enables you to do much more longer term planning. And so there are a lot of sorts of things that we can talk about that might push you in the direction of doing more or less optimization.
That's interesting. One thing you actually mentioned there that I found pretty interesting was the idea of compressed policies and things like that. So it seems like in some ways, if we were to speak of maybe things like the Kolmogorov of complexity as a kind of measure, then just having a single algorithm that our model finds as an optimization, as you said, like MCTS or something like that for solving Go, might be a little bit simpler than if we were to go ahead and write out and specify in the first place, okay, you're going to use MCTS search or something like that, and then kind of go ahead and specify further from there, if that makes sense. Maybe I'm going in the wrong direction with that, but I think that's a pretty interesting point to think about.
Yeah, I absolutely think that I think we should be expecting that at some point our model is going to be learning these powerful optimization algorithms, and we need to figure out, how to deal with that. And one way to deal with it is to be we're going to really tightly control what sort of optimization it does. We're going to hard code that optimization and understand what the objective is that it's optimizing for. That's one way to maybe try to deal with this problem. There is some concern that in that situation, maybe if you don't give it the right sort of optimization, it'll still just learn additional optimization itself. Because, if you're still just doing this very general search over possible parameterizations, you might still be the case that additional optimization is going to be a thing that is good to find in that situation that's going to give you better performance. So you might still find optimization even in a setting where you sort of explicitly gave it optimization as well, if it's just sort of more optimization is necessary.
Mm-hmm. So there's a couple of things I'm curious about here, actually. And I think, so the first is, this definitely seems like we've, of course, started to see, I guess, ideas that start to trend toward this. So if we look at like neural architecture search and auto ML, that's maybe not quite, getting to some place where we have MESA optimizers, but we are still doing a search over maybe I've restricted my search space to specific types of neural network architectures and things like that. And then we do some kind of optimization for what precisely that looks like. And that's not quite MESA optimization. But one thing that this makes me think about is that these procedures have been found to be very, very computationally expensive, right? Almost to the point where they're prohibitive for almost anyone except basically a giant like Google to do, for example. So one thing I'm curious about is maybe just about how feasible this is. So even before we get into maybe theoretical reasons why we might expect MESA optimizers to be likely, practically, this feels like it might be the outcome of some incredibly expensive search procedures, because to have an algorithm where we end up with a MESA optimizer in the first place, it seems like the search space that our algorithm is going to have to look through is probably going to be pretty incredibly large if it includes things like optimizers. And maybe I have the wrong thing there, but it seems that way to me. And so that makes me wonder if when people try to develop algorithms of that sort, or if that happens, whether there might be a restriction on whether we're even able to do that by virtue of the fact that it might just be so computationally expensive.
Yeah, I absolutely expect that the first places where we see these sorts of really powerful optimization algorithms being trained will be situations where, whoever has access to the most computational resources and the most sort of ability to run these sorts of really large training processes. There is definitely this sort of interesting question of, at what point do we end up with models that are large enough that they could learn something like optimization end to end? That's a really tricky question. We know from a theoretical perspective that, neural networks, arbitrarily large neural networks are, universal function approximators. And so theoretically, eventually, we should expect they probably should be able to. Exactly at what point is really unclear. You could make an argument that, something like GPT-3 maybe is already a MESA optimizer. It has, the ability to do a lot of, powerful optimization on downstream tasks, where you can ask it questions that are like, how would we, do some other thing that wasn't exactly what it was trained on, and has the ability to solve a lot of these tasks. Maybe it's using something like search or optimization to do that. We don't really know. One thing that we do definitely know is that there has been work demonstrating the phenomenon of capability generalization without objective generalization that I was referring to previously. And in many ways, the reasons that I would expect something like MESA optimization to be dangerous is because I expect that it might cause this sorts of capability generalization without objective generalization, where the optimization algorithm that you learn might be more powerful and sort of, might generalize better than the objective that you learn to use it on. If the training process is insufficient to really give you a good objective, but it's good enough to give you a really powerful optimization process, then when you generalize, you'll end up sort of with this capability generalization and objective generalization. And this is something that we have seen. So there's a recent NERPS paper that was sort of going into very explicitly studying capability generalization and objective generalization based on on our risk-limited optimization paper, where what they went into was that they were able to discover that they trained a bunch of RL agents in these various different environments. An example is the sort of a coin run agent on this sort of, trying to play this game, get these coins. And they found that the agent, in a lot of circumstances would learn to navigate the sort of really good at all these various different coin run tasks. But it would often learn things like, rather than actually trying to get the coins, it would learn things like just go to the right of the screen, because the coins, were always on the right. And so it sort of, they were able to demonstrate they could learn these really powerful policies that really know how to navigate lots of different possible coin run environments, but they were navigating them for the wrong purpose. They were navigating them to try to get to the end, to the right, rather than to try to get the coins.
That's a really interesting case. And, I guess I kind of have two questions at this point. So the first one is maybe to a little bit earlier when we were thinking about the danger of Mesa optimizers. One thing I'm curious about is how we might even detect the presence of a Mesa optimizer, what that would look like. Because sometimes I expect, I might not know exactly what my model is doing internally. There's a kind of epistemic barrier going on there. So I'm curious how we might detect something like that. To this NeurIPS paper, and I think the example you gave earlier of the maze and the green arrow, I think those are both really great examples because we can see clearly how, I think what sticks out to me, I suppose, is that at training time, it seems like we're not carefully curating what exactly our algorithm might be getting. And so this might start getting into some of the adversarial training ideas. But I'm curious if, a potential beginning to a fix of this capability generalization without objective generalization is just being really careful about how we curate the training examples that we give to our RL agent or whatever thing we might want to optimize.
Yeah. So I definitely think that this is like the right line, the sort of right line to start thinking along. But I do feel like, so I think there are some issues that you start running into when you start sort of going along this route. And I think that, so one thing that I would point out is that it's not always the case that you actually will learn, even if theoretically you have enough information in the training data to distinguish between going to the green arrow and going to the end of the maze. It doesn't guarantee that you actually learn the right thing. And in many cases, you might still learn the wrong thing because there might be, it might be, for example, like in the coin run case, maybe specifying the right of the screen is much easier than learning some complex policy to figure out where the coins are. And so even if there are situations where theoretically, going to the coin rather than the right of the screen would give you more, reward, it might still learn just to go to the right of the screen because going to the right of the screen is simpler. And we know neural networks are just biased towards simplicity. And so if there are situations where it learns some simpler policy than the one we actually intended, some simpler objective, if in the case of a Mesa optimizer than we intended, that could be a big problem, even in situations where theoretically there's enough data to distinguish between them. So I think that, one really interesting example of this sort of thing is that there's sort of an analogy here where we can think about, evolution. Because we as humans were produced by a sort of evolutionary process that selected us to, maximize our inclusive genetic fitness, have as many children as possible, pass on our sort of DNA into future generations. But that's not what we care about. Like when you ask humans the things that they want, they're like, I want happiness and love and, beauty and, all this random shit that is like not what evolution was selected for. And so we can sort of ask the question, just like, well, how did that happen? That evolution sort of selected us for one thing, and yet we ended up caring about a different thing. And I think that one way in which you can describe what happened there is that we learned simple proxies for what evolution wanted us to learn. If you think about something like one example I like to give here is, let's say you have a baby, and this baby is in this alternate reality where they actually learned to care about how much of their DNA is like in the next generation, and the baby like stubs their toe, and they have to do some like complex calculation that is like, okay, how does my toe being stubbed impact my ability to pass on my genes? Like maybe this will make it harder for me to go hunting because I won't be able to like run as fast. Maybe, or maybe actually by stubbing my toe, I'm going to get a chance to stay at the tribe for longer and I can meet more mates or something, like has to do this really complex calculation. But evolution knows the answer, right? Evolution has done a lot of, trials of this, and it knows that stubbing your toe is generally bad for your genetic fitness. And so it's like stubbing toe causes pain, and pain is bad. Whenever you get pain, you should avoid it. And so, you might think that theoretically, in all possible environments, avoiding pain isn't going to be as effective at getting your genes to the next generation as like actually if you cared about getting your genes to the next generation. But it's way easier to calculate. You just have this like neuron that just like fires whenever your like toe gets hurt, and you just like that gives you a negative signal. You're like, don't do that. And so in some sense, we can sort of think about, what happened as, we learned these much simpler, easier to specify, easier to calculate, easier to use proxies like avoid pain, rather than the sort of, much more complicated thing like, get as much DNA into the next generation as possible, even if theoretically getting your DNA into the next generation was sort of the thing we were being trained on. And so I think that this sort of suggests that there can be situations where you can learn something that is much simpler and much sort of faster than the thing that you really intended, even in the presence of enough data to distinguish between the two.
That's really interesting. And I guess what that speaks to, thinking to the analogy you made, is that for the baby and for the RL agent, it's maybe better, as you said, given the bias towards simpler functions, towards simpler solutions, to learn these proxies that, as you said, are a lot more immediate, a lot easier than computing the whole what's going to happen to me over the next few states, over the next few generations, years of my life. And while those may indeed correlate with what the final objective is, we can't make claims, especially in complicated enough systems, about the causal relationship between things like stubbing your toe and passing your genes on to the next generation. So sure, by proxy, it's like this might definitely be bad for me, but then also we can make a causal claim that this is definitely going to stop me from passing some genes down to the next generation. And so in the same way, it's like for the RL agents, whatever proxies they might be using to distinguish between things, that might not necessarily actually help them with trying to apply that knowledge towards optimizing what the original objective was then. Cool.
Yeah, that's exactly right. I think that there's sort of something going on here where it's not just also, and this is something that I also want to start pushing, but this is sort of another whole topic in and of itself. But I also want to point out that there is another interesting thing that can happen here, which is, I think once we really start pushing on it, we're like, theoretically, if we just train on all the possible, ways in which things could be different in different environments and really force it to, if we train on enough possible examples, we can sort of overcome this natural bias towards simplicity and, force it to learn a more complicated algorithm, that fits the data. But there's a concern that I think things can start to get a little tricky in this case, because fundamentally what gradient descent is doing, what machine learning is doing, is that it's just looking for some parameterization of a function, some algorithm, such that the algorithm looks like it does the right thing on the training distribution. But machine learning doesn't give us any guarantees about whether it's doing the right thing for the right reasons. And there's a lot of bad reasons that you might have for doing the right thing. And so, an example of a bad reason that a model might have for doing the right thing, and we're only selecting in machine learning for doing the right thing. We don't care, it doesn't care about whether it's doing it for the right reasons. There are some really bad reasons. So one possible really bad reason might be that actually the algorithm has just learned to, one simple thing would be it has just learned to accumulate power. And so it's like, well, probably I'll be able to do the most stuff in the world and get the most power if I do what this training process wants me to do. Mm-hmm. And that looks like it has really good performance on the training distribution. And it's really hard for you to tell if it's doing something like this, because it looks like it's doing the right thing, but it's clearly doing the right thing for the wrong reasons. And the problem is that machine learning structurally only selects for models which do the right thing, but not for models which do the right thing for the right reasons. And so you can end up in situations like this where it's doing the right thing, but for a really bad reason that even if you have, in some sense, even if you had arbitrarily large amounts of data, you wouldn't necessarily be able to tell if it was just trying to, accumulate power or something, do something that was something that it's trying to trick you or something. Now, I think accumulate power example is a little bit weird because that's like, well, why would it ever want to do that? We can talk about more realistic cases. I think they exist. But I think that the sort of more general point is just that it's interesting that, there are a lot of really bad reasons that you could have for doing the right thing that machine learning is perfectly happy to find models with those properties. But then when they generalize, things can get bad.
Mm-hmm. Yeah. One thing this makes me think about, and I suspect this might not be totally on the alignment front, but I know that some folks have spoken about them in this regard, is I think there's been a lot of discussion about the impact of like recommendation algorithms and all of that recently. And I think that the way some activists like Tristan Harris put it, even if I find their characterization a bit bleak, is something like the recommendation algorithm is tasked with something like, let's increase our viewers' watch time, or let's have our viewer engage with the site as much as possible, dependent on whatever objectives we want. And in, I think, Tristan and a couple of other people's view, the recommendation system solution to that is, okay, well, let's try to warp my users to make them as predictable as possible, and then kind of turn them into these like machines that we can just send along whatever browsing paths we want, or drawing them into producing more ad spend for us, which maybe is a little bit of a bleak way of putting it. And I think, maybe ascribes a little bit too much cognition on the part of the algorithm, at least the ones that exist today. But it sounds to me at least a little bit similar to the story you're telling about these potential, I think this is what you're describing as basically deceptive optimization process, right?
Right. I absolutely think this is a fascinating example. So David Kruger, who's I believe a associate professor at Cambridge now, he has a paper that sort of goes into this sort of understanding, what sort of can happen in these sorts of recommender systems like you were describing. And there's something really interesting here. So I think that one of the things which I think, we oftentimes like to rely on when we do sort of machine learning setups is that we rely on this sort of assumption that, when we reset the environment, we have like a new episode or a new sort of step, things are actually reset, that there hasn't been some like carryover, and that our sort of model isn't going to be trying to optimize for anything across episodes. Mm-hmm. But what we find is that actually, and what sort of David finds in this paper is that actually, in a lot of cases, for a lot of different algorithms that we sort of very commonly use, including population-based training and even just vanilla Q-learning, they can learn to do things where they actually learn a policy which is optimizing across episodes, which is trying to, do something in one episode, which is like, for example, change the human in some way that makes the task easier in the next episode. And they learn this policy because of the way in which doing that is correlated with having done it in the past. And so because of this, the like population-based training, for example, will just be like, the algorithm which generally does this thing overall on average performs better. And so we select for it. And what's so scary about this is that this is exactly the sort of thing which can lead to, I was sort of alluding to earlier, maybe a more realistic example of this sort of deception. Because if you have a model and that model cares about some objective across, episode boundaries, if we think about just the maze example, let's say it cares about going to the green arrow, not just once, but as many times as possible across episodes and across time. This model is much more dangerous. And in fact, what this model will do, if it has an understanding of the training process, which we should probably expect if we're training, it on a huge internet corpus, at least of, including Wikipedia page on machine learning, and it knows how all these things work. Mm-hmm. It should have an understanding of the training process, and it should know if I don't go to the green arrow during training, if I go to it, then gradient descent will keep me the same because I did the correct behavior, I did the low loss behavior, and so I am a model which is sort of consistent with the sort of having good behavior on the training distribution. But if I go to the green arrow, if I do the wrong behavior on the training distribution, then gradient descent, the training process, will modify me to be different so that I don't go to the green arrow in the future. But if you have a model that has this sort of non-myopic objective that sort of spans episode boundaries, where it wants to go to the green arrow as many times as possible, then you're in a situation where the optimal policy for this model is to go to the end of the maze during training so that it doesn't get modified by the sort of training process. And then during deployment, go to the green arrow as many times as it can. And that's really scary because now we're sort of incentivizing, this sort of model is incentivized to trick us. It's incentivized to trick the training process. Mm-hmm. And so if we're in a situation, and I think they sort of, what this sort of problem in recommendation system is suggesting is that it's suggesting that this, it's sort of a proto example of this sort of deception problem where it's like, it's showing that models will learn behavior where they can make some modification, do some change such that they get better behavior, they get better performance way later down the line, by like modifying the human so the human becomes easier to predict in the future, or by, tricking the training process so that they don't get modified and they can do better things in the future. When you have models that are learning these sorts of behaviors, they're sort of, they can easily slide into each other. So, maybe, right now we're sort of seeing recommendation systems that, have these really non-myopic policies where they modify humans to like make their task easier. And maybe in the future, we'll start to see systems where the way in which they sort of make their task easier in the future is by, tricking the training process. Mm. And so I think that this is like a particularly sort of dangerous and interesting case. And I think that I totally am in favor of like trying to understand how we can better prevent this sorts of non-myopia in recommendation systems, because I think it is likely to sort of directly translate into helping us solve similar problems that I think will occur later on as well.
Mm. Yeah, thanks for expounding on that. I think there's a couple of really interesting things in what you said there. And I guess we can dive into the whole myopia idea pretty soon, because I think that's another important thing here. One thing I'm curious about, though, is that especially when we look to more advanced systems, and I can't say it seems like this happens with recommendation systems, but one thing that I feel like a lot of this deceptive alignment hinges on is, as you said, some kind of understanding of the training process, or at the very least, some ability to know what's going on would be helpful for something that could possibly be a deceptive optimizer. And so what that makes me wonder, though, is how close we are to having systems that might possibly be able to possess that understanding. So you said, for example, if we fed something like maybe a language model, the entire corpus of the internet, and that corpus included the Wikipedia article on gradient descent, then maybe it's got an article in its training data that tells it about that. But to what extent can we say, that it really actually understands anything about that? Like the language models for today, if we look at GPT-3, I know there's already quite a bit of dispute over whether it actually understands anything that it's being fed as training data. So I'm curious
what you
think that looks like.
Yeah, so one thing that is clear is that the understanding is getting better, and that these language models are clearly getting more able to sort of answer really complex questions about, all of these sorts of domains. One thing which I will say is that I think that the sort of most concrete thing which I can point to, which like current language models really don't seem to have, which does seem necessary, is an understanding not just of machine learning and of training processes in general, but understanding of like themselves and what they are in the world, and sort of the fact that they are themselves in a training process. I don't think there's any reason that this is like fundamentally more difficult, more complicated, or harder to learn than anything else. It is, it's something that, especially if we're training models to like act in the world and do things in the world and help us in particular ways, which is something that we have been moving to as we've been, doing things like decision transformers and stuff, where we're sort of taking, language models and using them to help us do like RL tasks. There are situations where, we will eventually sort of presumably want models to have a model of themselves and understand what they are in the world. And that is, once you get to that point, then it has both an understanding of how training processes work, how gradient descent works, how machine learning works, and also of the fact that it itself is in a training process of this form. Then you're sort of, you're starting to get to the point where it could act deceptive. Now, it does also have to have this thing I was talking about how it has to have this non-myopic objective. It has to care about things across time. If it just cares about its own individual, like I want this output to be really good, then like it's not going to exhibit this sort of deceptive behavior. Mm-hmm. But the concerning thing, as I was saying previously, is that we see that a lot of the current training processes, like things like population-based training, directly incentivize models to have these sorts of optimization across episodes and whatnot. And so that is a pretty concerning situation to be in, where if we're sort of continuing along that path, we could end up in a situation where we are using these sorts of language model systems could eventually become quite dangerous.
Interesting. That makes a lot of sense. So there's one kind of other point that I want to think about a little bit before we get into potential ways to prevent deceptive alignment. And I think it was this. So in some of your posts, you've made a sort of counting argument here as to why we should expect MESA optimizers, why we should expect deceptive alignment to be likely, just by virtue of the fact that it seems like there are more solutions to a problem, more optimizers that would be deceptively aligned, as opposed to, say, robustly aligned, that are in line with that true outer objective. And so one thing I'm curious about here is, in the regime where we're dealing with MESA optimizers, and this is maybe referencing another one of your posts on how inductive biases kind of stick around once we get to this point where we have achieved zero training error because we have a sufficiently complex neural network or machine learning algorithm. And then it's starting to be able to achieve this sort of double descent behavior. And at that point, it seems like the inductive bias kind of comes back and starts to matter again. I'm wondering if there's maybe something a little bit different that occurs there beyond just a simple counting argument for deceptively aligned optimizers, whereby the inductive bias actually plays a part in how likely we are to have a deceptively aligned optimizer. I can imagine it might make it even more likely than a simple counting argument might suggest, since I think that it seems, like a uniform prior over optimizers. But I can also see situations where we might have a good inductive bias that makes it less likely. And I think you called this out as something to think about when we are considering deceptively aligned versus robustly aligned MESA optimizers, and how the inductive bias can make that a little bit dangerous. But I'm curious if you've thought a little bit about, I suppose it's hard to say concretely right now, but what sorts of inductive biases might be good in terms of steering us away from those more troubling situations?
Absolutely, yeah. I totally agree with everything you're saying. I think that there is, really trying to understand what are the inductive biases that push you towards something like deception or push you away from it is a really tricky problem. And one I think we really need a better understanding of the inductive biases underlying neural networks get at. I think one thing you were alluding to is the sort of, stuff I've written about thinking about double descent. And, what does double descent tell us about how the inductive biases of neural networks work? And I think it tells us a lot, and it certainly gives us some insight into the ways in which, for example, very large over-parameterized networks have this really strong simplicity bias. But I think that it's sort of clearly insufficient. We sort of really clearly don't understand what simplicity even exactly means in the context of neural networks. We know that there is some connection to things like command graph complexity, that, clearly things which are easier to specify are learned by neural networks more. But we really don't know much more than that. We really don't understand the extent to which these different sorts of, inductive biases sort of create the incentives for different sorts of models. Why would you get one model over another model if they both have equivalent loss? We don't really know how to answer that question. And so it makes it hard to sort of make sort of really concrete claims about, like, would you get deception? Would you get, any sort of possible dangerous behavior that you're concerned about? What we can definitely say is we can be like, look, the deceptive story that I was telling, is still a story where it has good training performance. And so at the very least, it won't be, selected against by the loss function. But we don't know whether the inductive biases will be such that it will be the one that we find with good performance rather than any other model which also has good performance. And this is a really tricky question. So, there are arguments we can make. We can be like, well, look, let's just imagine that it is kind of like simplicity, and be like, how simple is deception? It's like, well, the sorts of modifications that gradient descent would need to make to cause a model to become deceptive don't seem that complicated. Like, it has to cause it to have some belief that is like, it has some objective where it cares about things across episodes, across parameter updates. And, for example, go to the green arrow as many times as possible. So that's something that's required for deception. But there isn't much else. Like, presumably if it's in a situation where it just already knows what the base objective is, because it has to understand the world if we want it to be able to take actions in the world. And so it probably already knows the training process and understands the training process. So the only barrier to become deceptive is to actually believe that being deceptive will be useful to it. And as long as it believes that there's something it can gain from, defecting against us at some point in later on, then there is a reason for it to act deceptive. And so, the only modification that is necessary for gradient descent to make to the model is to just change it to, have some objective such that there's something to gain from acting deceptive.
Interesting.
And we can compare this to, what are other ways in which gradient descent, a model might be modified to have, good performance on the base objective. One possible way in which it might be modified to have good performance at the base objective is to just, gradient descent, just create some understanding inside the model of explicitly everything that it needs to know about the base objective. I think this sort of thing is just pretty unlikely structurally, though, because it has to, there's a lot of information in the input data, and we should expect that by default, it's going to reuse the information that exists in the input data. It's much more complicated to re-encode all of this data about, we're trying to train the model to, do good things. It reads the Wikipedia page on ethics. Why would gradient descent, it has both encode for what's knowledge necessary to predict the Wikipedia page in ethics, and then re-encode an understanding of actual ethics. Presumably it's going to reuse that information. And so deception is one way of reusing it, of giving the model some simple objective and then having some modification to it such that it becomes deceptive in sort of service of that simple objective. Is sort of one way of making use of the fact of going from a model which knows what the sort of objective is that we're training on to a model which actually cares about that objective. The problem is that the deceptive model cares about it for the wrong reasons. But of course, gradient descent doesn't care. Machine learning doesn't care about whether it cares about it for the wrong reasons. It just cares about whether it cares about it, or whether it looks like it cares about it, right? Mm-hmm. Another way to think about this is there's sort of an example that is we can think about, an interesting thing is consider a duck, okay? And a duck has a child. A mother duck has a duckling. And the duckling needs to figure out who their mother is so that they can, follow their mother around and do all this stuff. So how did the duck learn to do this? Well, it learned to do it via this sort of imprinting behavior, where it sort of looks for the first thing it sees, and it's that's my mother. Mm-hmm. And then I'm going to follow that around. And you can think of this sort of imprinting as an example of a way of, rather than sort of the duck having explicitly learned, what it means for a thing to be a mother, all it learned was at some point, you're going to have to build models of the world. And at some point, your model of the world is going to include your mother somewhere. And we know that probably the first thing you see is going to be your mother. And so this is a way of reusing the model's knowledge about the world and turning it into sort of a way in which the model actually starts optimizing for the thing we want it to optimize for. And so I sort of call this the corrigible case. This is the sort of case that, if we actually learn this sort of pointer to the correct behavior, in the same way that a duck has sort of a pointer to its mother in its sort of model of the world, it's sort of the first thing that it sees, this would be pretty good. And so you can think about, I think, the sort of deception case and the sort of this corrigible case as two different ways of going from having a model of the world that includes what objective you're being trained on to actually caring about or looking like you care about that objective during training. And the concern is that, I think that deception might actually be simpler than the corrigible case, because in deception, you just have to have this objective that is long-term. Whereas in corrigible, building a pointer like that can be kind of hard, because you have to, make sure that the pointer is actually robust and is pointing to the right thing. If we think about ducks, for example, imprinting goes wrong a lot of the times, and so if we have diverse enough training environments, we're really trying to force it to actually get the right thing in all the training examples. Imprinting might not be good enough. It might, imprint on the wrong things. Mm-hmm. And so deception, though, is very robust during training, because if a model that is trying to, do what the training process wants for the purpose of being selected for by that training process, if it finds that its notion of what the training process wants to do is different than what it actually wants to do, than what it thought it wanted it to do, it will just change. It'll realize that, actually my notion of what the training process wanted was wrong. It actually wants this thing instead. I should do this thing instead. And so it's very robust. If it learns new information, it'll just do the right thing automatically. Whereas the corrigible one won't. If it learns new information about if it learns, actually your real mother was this duck over here, not this one that was this human that birthed you or whatever, artificially, then it doesn't care, because it's already imprinted on the wrong thing. Mm-hmm. And so I think there's a lot of arguments we can make like these, where we can, talk about why might it be the case that your model would you would learn one sort of behavior or another sort of behavior, one, potentially dangerous behavior over potentially safe behavior. But fundamentally, like I was saying at the beginning, all of the arguments I just made are pretty suspect, because we just don't understand what this simplicity really means in the context of neural networks. And until we get that understanding, it's just super hard to predict which of these sorts of things is going to be simpler or more likely to be selected for by our training processes.
Mm-hmm. Yeah. And I think another thing that what you said really calls out too is the need, I guess this isn't the same thing as understanding the inductive biases, but even interpretability as far as understanding the reasons why our algorithms are making certain decisions. Like we've already gotten the beginning of model monitoring and interpretability. And of course, for very basic models, you can obviously just look at the coefficients of like a linear regression and kind of see what's going on there. And then for convolutional neural networks, I know there's ideas like saliency maps, what part of the image does this neural network find very important and then modify its gradient, for example. But especially as we develop more and more powerful systems, and even things like GPT-3, I can imagine this is why a group like Eleuther AI thinks that needs to be open source and more people can study it. Finding ways of attacking these more and more complicated models with interpretability tools to better understand what's going on inside that black box is going to be more and more vital, especially as we expect to be getting close to a world where MESA optimizers might start arising.
I absolutely agree with that. I think that interpretability is like a really promising direction for trying to sort of, I was sort of hammering home that like when we do machine learning, it selects for models which do the right thing on the training data, but not necessarily for models which do the right thing for the right reasons. But interpretability gives us the option to change that. It lets us potentially understand what the reason was that the model did something. And if we can know what the reason is, then we can start selecting for models that don't just do the right thing, but do the right thing for the right reasons. And I think that is critical for our ability to, really train systems that, are generally safe, that are able to deploy them in lots of different settings and they consistently do the right thing because we know why they're doing the right thing. And we know that the reason they're doing the right thing is the right one. We know that they're not doing the right thing because they're trying to trick us, because they just want to get deployed later. They're not doing the right thing because they learned some proxy, like they learned to go the green arrow around the end of the maze. We can figure out that, actually they're doing the right thing for the reason that we intended. And I think that fundamentally that sort of opening up the black box somehow has to be the way we solve this sort of problem. That if we are just sort of confined to dealing with machine learning systems as black boxes, we just will not be able to figure out why a system is doing some behavior on the training distribution. And if we can't understand why it's taking some behavior, then we just can't, then it's sort of not going to be possible, I think, for us to be able to ensure that its generalization behavior is going to be correct. Because it could be doing the correct thing. It could look like it's doing the right thing. And gradient descent is happy to select for a model which looks like it's doing the right thing for a totally incorrect, bad reason.
Yeah. I also agree that it's a very important aspect of generally safe systems. Before, the last thing I kind of want to get onto is some more solutions to this. So talking about relaxed adversarial training and perhaps a bit about myopia. But before we do get onto that, one thing I'm curious about, if you've thought about this, and I know there's some people in the AI alignment space that do, is just the fact that thinking about these interpretability concerns, adding additional monitoring, things like that, that is an increased burden on the folks who are deploying, who are using ML models. And so I think the question then becomes, okay, how do you incentivize people to actually make use of these tools in the ways that they're intended? One thing that I came across pretty recently was this really interesting study about folks who were, given interpretability tools, and they thought that they kind of understood what their models were doing, but really they were just looking at these interpretability tools as a kind of checkbox thing, like, hey, I quote, understand how my model is working. And it turned out that, they really just had a bad understanding or no understanding at all. If anything, sometimes these interpretability tools gave them misconceptions about how things were working. And so as important as they are, I do also worry about the human side of the equation. Even if we end up with great interpretability tools, how can we start ensuring, they're being used in the right way and are achieving, the results we want them to? I'm curious if you've thought about that side as well.
Yeah, I absolutely believe that this is, a really tricky question is how do we actually sort of ensure that interpretability tools are telling us something meaningful? Like you're mentioning, there's a lot of situations where they tell us things that end up not being meaningful. This paper, the sort of interpretability illusion, that's sort of going into these sorts of problems. And I think that, there's a lot of ways in which we can talk about trying to address this sort of thing. I think that one thing that I'm excited about is ways in which we can try to, find models which are easier to interpret. I think that, we don't want to just be sort of, I think a lot of times in sort of machine learning, we are in a situation where it's just like, we have, we use the neural network architectures that we use because they give us good performance. Mm-hmm. But we don't really look at the other arguments for and against using some particular architecture. And one thing I would be excited about is trying to understand, what if we moved into a sort of situation where actually the reason we used particular architectures was because they were easier to understand and easier for us to interpret and didn't give us, make it so that we were really confused when we tried to apply interpretability tools to it. Mm-hmm. I think there's a lot of low-hanging fruit in this sort of domain. And I think that's one way in which you can start trying to address these sorts of problems where it's like our interpretability tools really just give us totally incorrect answers.
Mm-hmm. Yeah, that sounds like a really exciting direction to go. I think the thing that I always think about in this regard is, the kind of people incentives, right? So we know that there's that interpretability performance trade-off. And so I guess it's possible that more powerful neural network architectures, ones that perform better, could generally be less interpretable. Although it does sound like some recent research has started to fight against that. So I know there was a recent study of, I think it was ImageNet, that found a lot of pretty striking, mistakes in it, and then found that when they trained a bunch of neural network models on the actually fixed up ImageNet, that it seems like some of the simpler, easier to understand neural network architectures actually performed better on that fixed up ImageNet. And so I'm curious if research like that gets pushed forward enough, that maybe there might be enough of an awareness that, these super complicated architectures maybe actually aren't what we even should be going for in terms of performance either. So I would be very excited to see, the day that gets pushed forward and we see a world in which we are picking architectures not just for as close to 100% accuracy as possible, but also that interpretability aspect.
Right. Well, one thing which I feel like I want to emphasize here is that, I think a lot of times sort of machine learning researchers have this sort of, background assumption that, the thing that's really going to matter is performance. Mm-hmm. And I think in the real world, this is just often not true. Like the things that a lot of people big organizations and a lot of the use cases where we want, machine learning for, oftentimes one of the really important things, that those sorts of people will ask for is, I want to know why it's doing what it's doing. And a lot of, for example, critical infrastructure types of situations where we sort of deploy models. If we're deploying, we don't just care about performance. Even just from an economic standpoint, what are the actors in the world going to ask for when you're like, I've built you an AI system, here you go. One of the things that I think a lot of them are going to ask for is, why should I trust it? What is the reason to believe that this thing is going to do the right thing? And I think that moving in a direction where the sort of machine learning community understands that, performance is not the end all be all. That actually, when we go to even just use these systems in the real world, being able to say, I know why the system does what it does, and therefore I know when it will fail and when it won't fail, is really important and a really just practically relevant thing to have to be able to, want to use a system. And so I really do think that, even just from a perspective of just practically, what is going to be useful in the short term, not even just from a existential risk perspective, it's really going to be important. I think we should be emphasizing more the sort of importance of being able to understand why our models are doing what they're doing.
I totally agree with you on that. And, I think it still is even a little bit of a paradigm shift from where we are currently, because if you look at a lot of the applications of ML today, in medicine and hiring, for example, I know one company that has been under a fair bit of scrutiny and controversy is HireVue, right? And they claim that their hiring algorithm is sort of able to scan your video and take in thousands or tens of thousands of features into account. And that sounds like something that is notoriously uninterpretable. And in spite of the fact that I believe Illinois has put laws in place that are like, you should be more transparent about this. Job seekers aren't actually going to learn that much more about how the algorithm is working. And there's so much going on and, how do you game these algorithms? But still, they're so complicated that folks don't understand how they work. And HireVue's pitch is not so much on the interpretability side. So I do wonder, and I think it seems like there's definitely a bit of a trend towards folks asking for more reasons why these things are working. So my hope is that maybe that incentivizes the companies like HireVue to perhaps trend towards crafting algorithms that are more interpretable, besides ones that, just maybe meet up to some arbitrary standard of accuracy that doesn't actually matter. And especially in situations like hiring, even that level of accuracy doesn't actually make sense all the time, right? Because in the case of hiring, for example, you are measuring up to standards that have been crafted by humans who are making faulty decisions over history. And so in that respect, of course, you've got the algorithmic bias situations, all of those buzzwords people talk about. So I do think there's a little bit of a paradigm shift to be had there before we get to this point, but it does seem like there is a push in that direction, which is really positive to see.
Absolutely. Yeah, I definitely am excited about this. I think there's a lot more work to be done and a lot more that, all of us can do to try to push for, more transparency in machine learning systems. But I definitely am excited about these sorts of developments. And I think that, also just, the more that we as a society ask for our machine learning systems to tell us what they're doing, rather than just, trust that, it seems like it has good performance, so we'll just use it. I think this also pushes machine learning in a good direction, which is towards really trying to figure out why the systems do what they do, and understand, why they'll be actually be correct in certain circumstances and incorrect in others.
Mm-hmm. Yeah, absolutely. So I do realize we're going a bit long, but if you're okay with a couple more minutes, I did, before we sign off, want to just have you go into a little bit, your work on relaxed adversarial training. And, I think also another thing that seems relevant to this problem of misaligned MESA optimizers is that, multi-episodic sort of objective situation, and whether things like maybe a kind of imposed myopia could be a helpful solution to the problem without detracting too much from, the performance of an algorithm. So I guess first, if you could talk a little bit about relaxed adversarial training, that would be awesome.
Yeah, so I was sort of alluding earlier to this idea of, well, what if we have ways of building models that are themselves sort of more transparent? And I think that relaxed adversarial training is sort of trying to get at this idea, which is like, well, what if we sort of train our models to sort of satisfy some sort of property about how they work internally? Right? Train models not just on what they do, but why they do it. Have some ability to look inside the model during training and say, what is happening inside of this model, and is it doing the right thing for the right reasons? And if we like the reason, train on those reasons being ones we like. And I think that this is sort of relaxed adversarial training is getting at. And there is a sort of quirk to relaxed adversarial training, which is that it also incorporates this sort of recursive part, where we are using a sort of an overseer in this case that is not just like a human overseer, but also a sort of a human AI team overseer, where we are also training models to get better at understanding other models, so that we can, not just have all of the burden on being able to do this understanding fall on humans, but also, be able to train models and have AI systems that help us better understand other AI systems. And I think this is also sort of going to be critical because, we're going to get to a point at some point where, even if our interpretability tools are super good, we're still just not going to be able to, as humans, understand everything that's happening. But if we can, sort of bootstrap up to a point where we, are able to build models which we trust and then use those models to understand other models, then we sort of have a shot being able to understand even very large, very complicated, very powerful systems.
Okay, that makes a lot of sense. Let me think if I have any questions here. I think that is a really interesting process. I suppose what I do wonder is concretely what that combination of human machine understanding of other algorithms might look like. So I don't know if we have any good examples today, but to how you tie this back to the interpretability idea, the fact that humans might not understand everything that's going on, what would it look like perhaps for an algorithm to be able to understand another algorithm, if that makes sense as a question?
Yeah. I mean, I think this is a really tricky question, right? So I think there's a lot of, low-hanging fruit and progress being made on how do we make a model understandable to another model? I think there has been a lot of recent work trying to do things like, how do we, take a language model and let it also understand images or also understand music or, other domains. One domain that I think is really exciting is neural networks, understanding neural network weights and what neural networks do. And sort of, potentially in the same way that, we understand, that we sort of have models that understand language and sort of images. Now, this is a lot easier said than done. There's a lot of sort of technical difficulties that arise when you try to understand how would a model be able to make sense of, the weights of another model. But, it's something where I feel like there's a lot of work to be done, but there's also a lot of looking fruit. Like there's just not a lot of work being done on how do we do these sorts of translation tasks. Mm-hmm. And I don't know, I'm excited that there sort of is potential progress to be made there.
Mm-hmm. Yeah, given that it is low-hanging fruit, do you know of anyone at all who is starting to do work in that area, or something that, if a listener is interested, they might be able to look at to learn more?
Yeah. So there are I've been in some early talks with some organizations that are sort of looking for possible, new research directions. And so there might be some work happening along these domains at sort of some various new research organizations. But I don't know. I don't have anything concrete to talk about right now.
Sure. Cool. So I think just the very last thing I wanted to hit before we sign off on this is I think that other problem of myopia. So we've talked about how if we have these Mesa optimizers that have their own multi-episode objectives, whether they're recommendation systems or maze navigators or other types of algorithms, there's ways in which they might be incentivized to make these short-term sacrifices to look as though they're doing well in training distribution. And then they can, as you said, defect when they get out of distribution. So the kind of question I have here is whether a sort of imposed myopia is a possible solution to that problem. Maybe not a full solution, but a start at beginning to restrict the view forward of these agents in a way so as to stop that incentivization.
Yeah. So I think this is a really promising direction. And it's one that I think a lot about, which is, it's sort of the focus, I guess, of a lot of the research I'm doing right now, which is really on this question of how do we ensure that our models really only care about the one task that they've been given. If we're training a language model, how do we ensure that it really only cares about predicting the next token and is not trying to optimize for something else, beautiful sentences or something. How do we, if we have a model where we're trying to train it to just do if we think about like recommender systems, we just wanted to recommend the video that is best for you right now, not the video that would change you in some way such that it'll be easier to recommend in the future. What might it look like to have a system that is sort of doing something like that? And a lot of the sort of way in which I've been thinking about this is, we have to understand what would be the reasons what would be the sort of internal structure that a model could have that would cause it to do this in the right way. And I think this is really important because I think we need to understand what is the internal algorithm which we should be shooting for in terms of what we want our models to eventually be implementing. Because once we know what sort of algorithm we want them to be implementing, then we can talk about how to incentivize it to produce that specific algorithm. And I think we really need to be focusing on the algorithm, not the behavior, because we need to be understanding not just we want this particular behavior, but we want it to be doing this particular behavior for this particular reason because it's implementing this particular algorithm. And so one of the things that I'm thinking about a lot is how do we find a sort of type of decision-making algorithm such that it does, it takes these sorts of, always does the sort of myopic action. And I've been recently doing some work on this in the sort of context of decision theory. And so I recently published some work with Adam Shimi, trying to sort of go into what would a decision theory look like that is sort of myopic in this way.
Interesting. Cool. I think that's a great start just to start thinking about these issues. I don't want to keep you around for too much longer. So, just as a final thing, for listeners who might be interested in learning a little bit more about your work, reading about myopia, about inner alignment, where can they find you?
Absolutely. So I publish most of my work on the alignment forum. So this is, you should be able to just Google alignment forum. You can really just Google alignment forum and my name, and you'll find my specific work. I publish the majority of the work that I do sort of publicly on the alignment forum, where it's sort of accessible. I think the alignment forum is just in general a really great resource for getting more into and understanding what's sort of happening in the world of AI safety, because there's a lot of various different work from different people who work in AI safety that gets sort of published there. And so that's sort of a great spot to sort of learn more about what's happening in AI safety as well, both my work and also the work of, lots of other people in the field.
Fantastic. Well, thanks so much for all of your time, Evan. I do hope, the listeners here will go ahead and look a little bit more into your work. I personally find it really fascinating, so I hope others will as well. And with that, I think we'll go ahead and sign off.